Consider this scene from a movie from the 80s, but Val Kilmer's premiere, actually. So, obviously, the filmmakers were messing with your sense of perspective and your assumptions about what you were seeing, but it was a really good illustration of what we'll be talking about today, which is relative motion, and an illustration of why we say in physics over and over again that everything is relative. Everything that you are, you could consider yourself the center of your reference frame and the center of the universe, and you cannot conduct experiments which will distinguish that. Here, what we have, of course, is we're used to saying, oh, if the station is moving by us, we automatically assume that we are moving and the station's at rest, but you really couldn't physically distinguish those two things until you looked outside of the two. So, it's a nice little illustration. All right, this video goes into a little bit more detail over what we're seeing.
Imagine you are sitting in a moving train. You toss a ball into the air and catch it. To you, the ball went straight up and down. But to an observer on the ground, the ball followed a parabolic path as the train went past. This is because when the ball leaves your hand, it still has all of the forward velocity that the train does.
Not a great
But if
parabola.
you are inside the inertial reference frame of the train is not moving at all. It is the surroundings that are moving. So the ball no longer has any horizontal velocity, only the vertical velocity you impart to it by moving your arm to throw the ball.
All right, the rest of that video goes into some detail about relative motion, so if you want a further vantage point on it, it's worth watching, and you can find it linked on the class website. All positions are defined relative to some origin, hence, or as we say, at the reference frame. And since motion is a change in position, this implies that all motion is relative. You know that the Earth is also rotating. At the equator, the Earth's surface is moving about 460 meters eastward. At the latitude of Tulsa, it's about 370 meters per second eastward. So why don't you feel like you're zipping around at slightly more than the speed of sound? Because everything around you has that same velocity, more or less. So you only notice a small difference in the velocity of things, not their velocity moving relative to the Earth. In fact, the Earth is whipping around the center of the galaxy at about 230,000 meters per second, and the solar system as a whole is falling in towards the direction of Virgo at even greater speed. But all of these things are moving together, so they kind of drop out. We don't notice them. Now we're going to derive how that expresses itself. Imagine that Alice is sitting inside a train car that's at rest, and she tosses a baseball to Charlene. The velocity of the baseball, as far as she's concerned, is the delta of the position of the ball over delta t. Right? That v ball with respect to Alice is delta r of ball with respect to Alice over the time it takes. We're going to treat things as not accelerating at this point to get relatively easy answers. When there are accelerations in play, it gets mathematically more complicated and leads into much more deep physics than we're going to go to for it now. But anyway, here we're basically saying we have exactly how Alice, as a good physics student, would have defined the motion of the baseball. Of course, Dexter is an equally good physics student, and so he defines the velocity of the ball the same way, that it's the distance traveled by the ball as a vector over the time it takes. In other words, they would agree exactly on the definition, the physical definition of velocity. Complicated, though, is that Dexter sees the train car moving. In other words, when I said the train car is at rest, that's what Alice was considering. She was inside of it. But Dexter, on the road outside, watching it go by, sees it has some velocity. So, as seen by Alice, the ball simply moves from Alice to Charlene, no big deal. Neither Alice nor Charlene are moving, so the ball just travels the distance between them. But for Dexter, it's important to understand that while the ball is traveling from Alice to Charlene, Charlene is also traveling. She's also moving. And so the distance traveled by the ball is greater as far as Dexter is concerned. He would say that the ball, which starts here and ends here, has traveled a greater distance than the ball that starts here and ends here, because their actual motion of where we measure from has changed. If we were to plug that back into the equation, because we pick up some extra distance that is basically the velocity of Alice with respect to Dexter times the time, how much does Alice move? Because the amount that Alice moves is the amount that Charlene moves, so it's the amount of extra distance that's being added to the motion. And symbolically, we end up with what's called the relative motion equation. The velocity of the ball as measured by Dexter is the velocity of the ball as measured by Alice, offset by the velocity of Alice relative to Dexter. I want to point out what we've done here is we have this curious thing where Alice over here is in the subscript of one and the superscript of the other. The top and bottom positions of the subscript, I suppose, respectively. And so it's in some sense, we call this sometimes contracting the indices, where by putting together, by arranging them this way, they combine and Alice drops out of the equation and we just get the ball and Dexter acting on each with respect to each other. And so this will let us move from one reference frame, say from Alice's reference frame to Dexter's reference frame. Right? Notice we're measuring the same object in two different reference frames, and we do that by adding the apparent motion of the reference frame. As an example, let plus x be eastward. Alice can throw a baseball at 30 meters per second relative to herself. In other words, if she's on a pitching mound and she measures it, that's what happens. But the train car is moving past Dexter, that's relative to him, at 15 meters per second eastward. What is the velocity of the baseball as measured by Dexter? Pause the video and think about it for a sec, and then move on when you have an answer in mind. Well, using our symbolism from before, we see that the velocity of the ball relative to Alice is 30 meters per second, its speed, in the positive direction, the x-hat. And the velocity of Alice relative to Dexter and how fast the train is moving, which is the same as Alice's speed, is 15 meters per second in the plus x direction. And then the velocity of the ball relative to Dexter, remember we take what Alice says plus what Dexter thinks Alice is doing. So 30 meters per second x-hat plus 15 meters per second x-hat. Hey, the x-hats are just constants, so we factor them out, and we get the entirely unsurprising answer that Dexter would see the baseball moving faster than Alice can throw it. It's moving at 45 meters per second instead of 30 meters per second. What do you think would happen if the train had been moving westward? Well, in this case, if the train had been moving westward, then the train's velocity, and therefore Alice's velocity, would have been 15 meters per second in the minus x-hat. So we'd have minus x-hat here, or a minus, and we would have ended up with 15 meters per second. It would go slower, although still eastward. It gets even weirder if you imagine that the train were moving westward at 30 and Alice were moving eastward with the rainbow throw it eastward at 30, and then the ball would seem to hang out in space. Don't believe it? Well, luckily somebody went out there to demonstrate it for you.
So what are you so excited about?
Well, it's our turn to try a new type of myth, the physics thought experiment.
Great. Something to get the old gray matter working.
So here's how this one goes. Let's say you're driving along in a car at X miles an hour. You throw something out the back in the opposite direction at the same speed. Does it just fall straight down?
Build an air cannon, fire a soccer ball at 60 miles an hour. We'll do it again inside of a moving vehicle going 60 miles an hour. See if the energies cancel each other out, and we get a vertical drop.
Love it. Let's do it.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector edition! Yay! We canceled out velocity.
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
Okay, so there you go. The Mythbusters officially figured out that, in fact, it's true. Yay, relative motion. Now let's do something a little weirder. What if the train were moving northward, but Alice and Charlene were sitting in the same row, so that Alice still throws eastward? The picture here is a little goofy because I should really be drawing them from above, and I just don't know how to do this. So this is not an elevator moving upward. It's that they're both lying on their side for some reason, and she's throwing a baseball. In that case, the velocity of the ball relative to Alice would still be 30 meters per second x hat, but the velocity of Alice with respect to Dexter is the same as the train, which would be 15 meters per second y hat. And again, the assumption that y hat here is northward, not upward. And then the velocity of the ball with respect to Dexter is still the velocity of the ball with respect to Alice, plus the velocity of Alice with respect to Dexter. So we get 30 meters per second x hat plus 15 meters per second y hat. These are no longer the same variable. We can't factor out and add them. We can't do anything at all. But we can do a vector addition, and we can say that what would happen is we would have something which moved this way, and then half as strongly that way. And so what we would see is we'd see it tend to move both north and east along the line defined by those two things. This leads into what at least I call river and airplane problems, where we worry about things which are trying to cross some sort of stream that of a medium in which they move, so that they carry it south or whatever along with it. So for instance, here we have a stream, and the stream is moving southward at some velocity, apparently 2 meters per second is what we'll say. And let's say that the boat can cut through water at 5 meters per second. So if the river were still, the boat would move at 5 meters per second. Or, put a different way, relative to the water touching the boat right now, it's able to move itself forward 5 meters per second. But that water is carried by the stream downstream at 2 meters per second. And we might ask questions like, if the boat needs to end up directly across from a starting point, how should it be oriented? So we want to go from here and go directly across. Now we know we can't steer directly across because the boat will be carried downstream some distance. We'll need to steer upstream in such a way as to counterbalance that downward motion of the boat. All right, so how do we do this? Well, we want to say that the vector that we want, the boat relative to the ground, which should be, as pointed out, this one, it should go directly across, should be the velocity of the boat with respect to the water plus the velocity of the water with respect to the ground, so as to, again, contract out these indices. And so we know that our relative motion equation is going to set up this way. But then we can just draw it, can't we? We can just say, well, then the velocity of the boat with respect to the water is something upstream that we don't know, and the velocity of the water with respect to the ground is 2 meters per second straight down. Conveniently enough, we've picked that we get a right triangle, and therefore we can just say, well, this angle has to have a sine, which is 2 over 5. So we must head upstream at 23.6 degrees. The other kind of problem that you're often asked to do would be, what if the boat does head directly across stream? Let's take the equivalent picture. What if we had, in fact, had the person sail just directly across? What if the boat did just sail that way? Well, we know that it's going to end up going downstream by some amount and landing somewhere else. And we might ask, for instance, what is the angle that happens there when it drifts? Well, in this case, we would have that the boat travels directly across at 5 meters per second, but it's carried downstream at 2 meters per second. And so its actual motion relative to the riverbank would be like that. And I'm going to call that angle phi, and luckily we still have a right triangle. These are the two cases where you can just do the right triangle stuff, so life is a little easier. But now we're in good shape because we can say that the tangent of phi is the 2 meters per second against the opposite divided by the 5 meters per second of the adjacent, or 0.4, which means that phi is inverse tangent of 0.4, which turns out to be 21.8 degrees compared to the 23.4 degrees from before. You might think that it should be symmetric because now we're just heading downstream instead of upstream, but we're not really heading downstream, we're being carried downstream. The situations are not symmetric, and so we can't really use that argument. Instead, we find that we actually have to work a little harder, head a little bit more upstream to counterbalance the downstream tendency.